no new solid phase formation, right? So the minerals react into soluble products. And then incongruent dissolution is where you generally have primary minerals, and for us, right, that's largely aluminosilicates. Those aluminosilicates react and basically form into new minerals, and usually those minerals that we're looking at are secondary minerals, right? Because weathering reactions occur at Earth surface conditions, and the minerals that form at Earth surface conditions are largely our secondary minerals, and those minerals are clay-sized. So that's where we were last time, and I'm going to pull up some review slides from last time, and then we'll get into a deeper discussion of congruent dissolution. And one thing is I just found out about a meeting that I'm going to have from now on at 3 to 4, which is my typical office hour time on Wednesday. And so I need to change my Wednesday office hour permanently to 4 to 5. So I apologize if that causes any inconvenience, but it's a meeting that I have to go to that's related to curriculum. So today we're going to talk about some factors that influence secondary mineral clay formation. That is, what are a few, there's a lot of things, but we're going to talk about a few, just a couple important things that we can look at to make some predictions about the type of clay minerals or secondary minerals that are going to form an incongruent dissolution. And then we're going to talk after that about the fate of our cationic and our anionic weathering products. And this has a little bit to do with what we were talking about in the activity this earlier this week when we were discussing aluminum, right, and iron, and how aluminum and iron hydrolyze, right, and because they hydrolyze the water molecule so strongly, they end up precipitating and not being mobile anymore in the soil environment. Okay, so just by way of review from last time, right, we had our incongruent dissolution reaction. We have primary minerals, aluminosilicates, reacting with acid, which is the combination of water and CO2, forming our secondary minerals, right? And our secondary minerals are also joined by cations, right, that are from our primary minerals: bicarbonate, hydroxide, and silicic acid, right? And of course, silicic acid is the key to weathering. We must form silicic acid and then leach that out of the system in order for weathering to progress. Most of our primary mineral that are weathering are composed of some combination of those 7 cations, right, that you see on the list. And so today, right, Monday, we talked about some factors that influence here, some factors that impact dissolution of those primary minerals. In just a minute, we're going to talk about some factors that influence the type of secondary minerals, and then we're going to talk about likely fates of cationic and anionic products. So this is what we talked about last time, right? These are the factors that impact dissolution of those primary minerals, right? We went through that list and generated that list together last time, okay? So if we go to the factors that influence the type of secondary minerals, we can talk about a bunch of things, but we're just going to talk about this in terms of 2 main things. And the first one is the parent material. And the parent material is, the material from which our soil or our mineral is forming. And so this is largely dealing with our ingredients, right? So whatever constituents we have in our parent material, right, those are going to be the constituents that are going to be associated with our weathering products or our secondary minerals that are derived from those original primary materials, right, or parent materials. And so I'll show you some examples of that right now. And right, it's fairly straightforward here. Okay, so right, types of secondary minerals depend upon the ingredients, and these are the common materials, right, that we're going to find in the soil environment, right? Those are the 18 plant essential nutrients. Most of those are ones that we are given to plants by the weathering of rocks and minerals. And so therefore, those are going to be the ingredients, right, that are going to be found in our secondary minerals, except for, right, the ones that are in blue, right? Those are the ones that enter the soil through other processes largely, right? They're not derived from weathering reactions of our primary minerals, right? Those ones largely come from the atmosphere, either gases in the atmosphere or water, or in some cases, organic material, okay? So that's kind of a review from things that you learned in introductory soil science 121 when you took it, right? And so if we talk about, right, some common primary minerals, right, here's some very common ones that we find, you know, in soils that we would come in contact with. And right, these are all aluminosilicates. So there's some combination of aluminum, silicon, and oxygen, right? All of them have that. And then there is some other cations, right? And so when these weather and develop, those are going to lead to the formation of some secondary minerals that have similar constituents associated with them, okay? So, right, there's not too much that's complicated, I think, about that discussion there. Now, here are some common secondary minerals. That is, this is the molecular structure of those common secondary minerals, right? And you know that these ones right here are classified as one-to-one phyllosilicates, right? They have this tetrahedral layer right here, right, which is composed of silicon and oxygen. And then below that, down here, right, they have our aluminum octahedral layer, right? And the aluminum octahedral layer is just composed of aluminum, usually, and hydroxide. You can also get some other cations that are the central cations of that. But those form, again, because when they were weathering out of their primary minerals, the primary minerals had the ingredients necessary to form those secondary minerals, right? And these ones here, of course, are our 2-to-1 phyllosilicates. And these ones here are 2-to-1 phyllosilicates. And if those terms, 1-to-1, 2-to-1, or 2-to-1, don't ring a bell with you, or you never heard of them before, that's okay, because we're going to cover that in more detail later. But this is where, for those of you who had, and most of you did, right, rocks and minerals, this is where your background in rocks and minerals comes into play and is important and helpful, right? Because you covered these important types of phyllosilicates. Phyllosilicates, again, being our important secondary minerals that we find in temperate regions, right? But again, the whole idea here is that the ingredients that are present in the primary minerals are going to lead to some common ingredients that we find in those secondary minerals. Okay, so the next factor is climate, right? And climate plays a huge role on the types of minerals that are going to form, right? That is to say, the types of primary minerals that are then going to weather into secondary minerals. And of course, climate, we can relate that to wind, temperature, and rainfall. And we're just going to mostly talk about it in terms of temperature, rainfall. But we know, right, as we increase temperature and we increase rainfall, right, that leads to hastened weathering. Right, so climate, of the soil forming factors, right, climate is probably the most important one, right, in my opinion. So here, okay, so this slide right here, there we go. So this slide is just showing you where our warmest temperatures are on the globe on average, where you see the reds, right? That's where our warmest temperatures are. You can see that they're centered kind of around the center, or they're focused on the center of the globe because that's where the equator is, right? And the equator is just marked by the location on the Earth where it receives the most direct solar radiation. And generally, right in that area is also the area that receives the most amount of rainfall. So you got warm temperatures on average, and you got lots of rainfall. Both of those things lead to a greater degree of weathering. So typically, and in general, what we can assume is that as we go up in latitude in the northern hemisphere or up in latitude in the southern hemisphere, our soils are going to be less and less weathered, right? That is to say, and what happens with weathering? Right? What's one thing that we can predict that is going to happen along with weathering? Let's see here, Alana.
What was the question?
So what is something that we can expect to happen in terms of more intense weathering means what kind of property could we find or could we associate that with in the soil? And some of the things that I might think of is like, how can I relate clay content to weathering? How can I relate pH to weathering? How can I relate the extent of leaching or the extent of desilication?
So does that it decreases, weathering decreases pH?
Yeah, so right along the equator, right, in this zone right here, I'm gonna just move that up here, we expect low pH. What about clay content?
High?
High? What about secondary mineral content? And you don't have to answer that. How about you, Sinead? What about secondary mineral content?
Higher.
Yeah, right, because clays are the same thing as secondary minerals. Right, and in terms of desilication, right, we expect a lot of desilication, right, along the equator. So all these properties that I'm listing here, right, just a few of them, those are most common for where we have the most intense weathering, and where we have the most intense weathering is where we have the highest temperatures on average and the greatest rainfall. As we move north and south of the equator, right, to higher and higher latitudes, the extent of weathering is going to decrease. And so that means that the quantity of clay is going to decrease, the pH is going to go up, and the amount of desilication is going to decrease as well, right? And so the types of minerals that we're going to find in less weather environments are going to be more quartz or silicate rich, right, as a result of that. And that makes
I had a quick question about this.
Yeah.
What does this have to do with like the health of the soil? So like soils around the equator, are they more or less healthy compared to other locations in the globe?
That's a great question. So soil health has a lot to do with organic matter content and organic matter health. And where you have lots of organic matter in the soil, not always, but in general, those are locations where you have really pretty healthy soils. And because you have warm temperatures and lots of rainfall, that is a very good environment for a buildup of organic matter, right? And it's also a good environment for lots of microbial activity, which could lead to more mineralization and less organic matter in the soil. But in general, deposition of organic materials around the tropics is pretty high. And so those soils, right, if left on their own or if managed properly, can have pretty good soil health. One, or a couple confounding things associated with that is low pH. So those soils are pretty acidic. So that can make it difficult for the organisms that are in those soils to thrive. And they can be very leached in terms of nutrient content. So that also could lead to lower soil health. So great question. So let's talk about what a young soil looks like. So this is a soil that's going to be found in a desert region, so very little rainfall. And if there's very little rainfall, there's going to be very little weathering. And so here we do have an aridisol, and you can see the type of environment that it's in, but these soils are going to have lots of silicon in them. They're going to have high pH and not so much clay, right? Because weathering is less. As we move to kind of a moderately weathered temperate region soil, so we have some soils like this, not super close to where we are, but in areas that receive more rainfall than in San Luis Obispo County. And these soils, right, are moderately weathered. They have a bit of soil profile development in the formation of this E horizon, right? You know that it takes quite a bit of weathering to form that E horizon, but the idea here is that more rainfall leads to a greater extent of weathering. And then if we take it to the extreme, right, this is where we're going to find in the tropics, right, and in the tropical regions, our soils are going to be largely desilicated, super low pH, and by super low I mean about 4, and they're going to be super high in clay, right? And by very high in clay, I mean like upwards of 50% clay, right? Sometimes 60% clay, which is super high in clay. Okay, so let's talk about how we can put these two things together, parent material and climate. So just for context, in San Luis Obispo County, on average, we receive about 22 inches of rainfall per year. Okay, and most of that falls between November and April or so. All right, just for some context. So here we're looking at a map of a rainfall map of Florida, right? And Florida receives not exactly, but about 3 times as much rainfall as we get in San Luis Obispo County. And as a result, we would expect a greater extent of weathering, right? And maybe, that happening over hundreds of thousands of years, right? That could lead to the formation of some highly weathered soils like ultisols, maybe even some oxasols, because in Florida it's pretty warm temperature, right? Not all the time, but pretty warm temperatures most of the year. However, right, these highly weathered soils that are largely composed of oxides and iron and of oxides of iron and aluminum, right, like that you saw here, right, don't form in Florida. And even though the rainfall content, could lead you to think that they would. And the reason for that is because of the parent material. And much of Florida, like, it's pretty sandy, and below that is limestone or calcium carbonate. And limestone is a high pH material that, 1, buffers the pH, but 2, right, is not super rich in iron and iron oxides. And therefore, you don't form oxasols in that environment because the ingredients or the main minerals, the main parent materials there do not allow for it. Okay, so that's kind of putting together climate and our parent materials in terms of trying to predict the types of minerals that we're going to find, or the type of secondary minerals that are going to form from our incongruent dissolution processes. Okay? Okay. Any questions about that? So let us move onward now. So now we're going to talk about some factors or some things that we can look at to sort of understand what our fate of our cationic and anionic weathering products are, right? And our main weathering products, right, our main cationic weathering products are the ones that you see circled there, right? So we got sodium and potassium, magnesium, calcium, iron, aluminum, and silicon, okay? Okay, so, and the reason why I picked those, right, is because those are part of our list of most abundant elements in the Earth's crust. So those are the ones that we're going to kind of focus on when we're talking about, well, what's going to happen to these things once they're released in an incongruent dissolution reaction, right? Back to right, this reaction right here. Okay, so we're talking about those. And then we'll talk about the anions after that. All right, so, hang on a second here. Okay, so one way that we can look at the fates of our cationic weathering products and kind of make some predictions about what's going to happen to them once they weather is this thing called ionic potential. And ionic potential is simply a measure of the charge of our ion divided by its ionic radius. And the ionic radius is going to be in units of angstroms, which is 10 to the minus 10 meters. So y'all have your periodic table? You know this one? If you don't, that's okay. But the periodic table here that you have looks at and measures or has the ionic radii of all the ions in here, okay? And the units that they've given here on the periodic table are in picometers, which is 10 to the minus 12, okay? So if I ever ask you to calculate the ionic potential of an ion, right, make sure that you can convert picometers to angstroms, right? And how would you do that?
You would multiply by 100.
Opposite.
Oh, wait, picometers to angstroms. Yeah, you're right.
Yeah, so picometers, right, PM, which is 10 to the minus 12. All you do to get to angstroms is you divide by 100, okay?
What's the little A with the sign on top of it called again?
Angstrom. And it's named after somebody with the last name Angstrom. Okay? Okay, so let's go back here.
I actually have a quick question.
Yeah.
Just confirming that we're using the ionic radius for ionic potential and not the atomic radius.
Ionic radii, yep. So when we're looking at ionic potential, right, just remember the name. When we're talking about ions, we want the ionic radius. And charge, right, charge has to do with something being an ion. Okay, so ionic potential, right, can be related to mobility, right, of our cationic weathering products. And so if we have an ionic potential of less than 1, right, and things that fit into this category are things like potassium and calcium and sodium, you can see those. Those are fairly soluble in the soil environment. Weakly hydrating just means that when they're in the soil environment, because they're charged, they're going to pull water molecules towards themselves, and we'll talk more about that later. So they basically remain pretty soluble and stay in solution. As we move on to ionic potentials of 1 to 3, right, these are soluble, strongly hydrating cations, but largely when we're in less than 1 or 1 to 3, these are going to either stay in solution. The other thing that they can do is go on to cation exchange sites. Okay. Now, as we get higher in ionic potential and move to 3 to 9, right? These ones are easily precipitated, amphoteric. I'll define what that means in just a minute. They form oxides and hydroxides. And some good examples that fit into this category are like iron and aluminum, right? So we talked about iron and aluminum this week in the activity, right? They strongly hydrolyze the water molecule, and when they hydrolyze the water molecule, they form hydroxides, right? Or oxides, right? When we were talking about this in the activity this week, we said that when iron hydrolyzes, it forms this. When aluminum hydrolyzes the water molecule, it can form that, okay? And as such, right, these are solids or become solid phases, and they are precipitated and they're no longer mobile, okay? And the last one, right, that's critical for us, we've talked about calcium, magnesium, potassium, sodium. So calcium, magnesium, potassium, sodium are between less than 1 up to 3. Iron and aluminum fit in this 3 to 9 category. They're not mobile, right? They don't leach because they form these solid phases, these oxides and hydroxides. And then the last one is what? Which is the last cation that we haven't talked about yet. It's a super common component of most minerals.
Silicon?
Silicon. Brady said it. So silicon, where is silicon? There it is right there, right? Silicon is even higher, more highly charged than iron and aluminum. It actually is smaller, right? If you look on your periodic table, you'll see that it's smaller than the iron and aluminum. And because it's highly charged and very small, it forms super strong bonds with hydroxides, right? And oxides that are, or oxygens in the soil environment. And so instead of forming a solid, it forms an anion, right? So we know that silicon, one of the things it's going to form is silicic acid. And we know that this is aqueous, right? And we know that it has a pKa of about 9.7. And so in general, right, not totally true for everything, but in general, right, this is soluble and mobile, right? And that's true for the other substances that are in this category here, right? So some of these ionic potentials of greater than 9 species, they're going to form, some anions, right? And so what that means is that they're going to lose a proton. So if we showed deprotonation of our silicic acid, right, that would be H3SiO4 minus, and we know that that's not going to happen until the pH is, well, an extensive part of that is not going to happen until the pH gets up above 9.7, right, 9.8 and higher. I think we're going to get a lot of that happening. But the idea here is that since they're anionic or neutral, they're mobile and leachable, right? As opposed to the iron and aluminum that form these solid phases and are not mobile and leachable. Okay? Any questions about that?
Sorry, I missed when you were talking about what the numbers 1 and 1 through 3 and 3 to 9 are.
Okay. So those values, right, that you see in bold, right, those numbers are calculated ionic potentials. And the ionic potential, right, is just the ratio of the charge of an ion over its radius. So what we're saying is that we can group the ionic potentials of these different cations into these 4 different groups, right? And when they're grouped into these different categories, there's some common properties associated with each of them, right? So in group 1, right, those are pretty soluble and they're going to go on to cation exchange sites. In group 1 through 3, right, they are also going to go on to cation exchange sites and they're still going to be pretty mobile in the soil environment. And if you're in the group 3 to 9, right, they are not mobile. They form solids in the soil environment, and so they don't move and they don't leach. And if you're in the group that's greater than 9, those again become mobile and therefore they're leachable. And those are going to be our highly charged, fairly small cations. Okay, so we just use ionic potential to make some predictions about how mobile something is going to be in the soil environment and how it's going to react in the soil environment and what its form might be. Okay.
Thank you.
Yeah, absolutely. Okay, so I still need to go back to this term amphoteric, and I'll do that in just a moment. But if we talk about where our cation exchange sites are, right? So here you're looking at some clay minerals, right, in the shape of this kind of trapezoid. The dashed lines around it are negative charges. And because we have negative charges, that's going to attract positively charged cations. And a lot of the ones that you see, right, are calcium, magnesium, potassium, and sodium. Right? A lot of those are going to be there. You do see a little bit of aluminum in this diagram, but largely it's calcium, magnesium, potassium, and sodium. And that's because their ionic potential is the right magnitude that it's because they have this property, but one way that we predict that they have this property is by calculating the ionic potential. Right? That's what I'm getting at here. Now, aluminum and iron form solid phases. So here is what gibbsite looks like, right? AlOH3, right? And we know from the activity this week that aluminum reacts with 3 moles of water, form AlOH3 and release 3 protons. And this is important at pHs less than, Jack, less than?
I do not recall.
Catherine, less than? It's okay if you don't remember.
I do not recall either.
It's all right, less than 5.5, right? So that means that at pH above 5.5, aluminum is all like that. At pH is below 5.5, you're going to have some soluble cationic aluminum present. Okay?
Why does the pH have to be lower than 5.5 for that again?
Because aluminum has high charge and it is small, so that when it reacts with water, it pulls the hydroxide out of the water and reacts with it strongly and forms this solid phase. And at above pH 5.5, that reaction has essentially been completed. Okay? But we're going to talk about another thing that can happen with aluminum in just a second, and also iron for that matter. But we'll get to that in just a second. So let's go to iron. So iron, right? This is goethite. It's an iron oxyhydroxide. We know that iron will also react with 3 moles of water. And we know that iron is a stronger acid than aluminum is because it's smaller and it has a greater electronegativity. And that is important at pHs less than 3.5. Right? So pH is greater than 3.5, that reaction's been complete. That is, at pH 3.5 and above, there's not very much hydroxide present, right? But iron has such a high charge and small size that it scavenges the hydroxide out of water molecules. That is to say, it hydrolyzes the water molecule to an extent that it takes up all its charge with hydroxides and it's no longer soluble anymore. Okay, which is pretty awesome. Now, amphoterism, right? Amphoteric, right, just means that a species is soluble at low and high pH. Okay, so let's focus on aluminum here. So here we're looking at concentration, right, on the y-axis, and here we're looking at increasing pH on the x-axis. And we can see, right, that aluminum is soluble and exists as a cation at pHs less than 5.5. And then at pH 5.5, right there, it's pretty much gone out of solution, right? There's no more soluble aluminum because it's hydrolyzed the water molecule to an extent where all we have left is aluminum hydroxide. But then, as we raise the pH, right, so I'm just following this line right here, as we raise the pH above like 7.5 to 8, right, we get a soluble anionic aluminum hydroxide species. Okay? So that's just demonstrating that aluminum, right, is soluble both at low and high pH. And that amphoterism is also dictated by its charge, its size, and another property called its electronegativity. We will get into how these 3 properties of all the cations and all the ions in solution kind of make them behave like they do. Now, iron is amphoteric too, but when we get an iron hydroxy anion is beyond the scale of this slide right here. That is to say, it's well up above 14, right, where we get iron hydroxy anion. Okay, so aluminum is our common amphoteric cation that we find in the soil environment. Okay, pretty cool stuff, I think. Now,
is it only aluminum and iron that are like that?
Yeah, largely. Like aluminum and iron are the dominant ones that do that, and iron really is not that important because it doesn't form an anion until pH is above 14, right? So that's not going to be important in the soil environment because the common pH range of the soil environment is like 4 to 9, right? So we're not going to see iron really as an anion, iron hydroxy negative charge. We won't see that. Okay. So here, this slide right here is just demonstrating kind of what I was just talking about, the amphoterism of aluminum. So up here, when we have a pH less than 5, we got this aluminum, AlOH, with 2 positive charges associated with it. And at pHs greater than 9, we have our aluminum hydroxide anion, right? Demonstrating aluminum's amphoterism. Okay? Good? I assume that that's good. All right, let's go and talk real quick about anions, right? So fates of anions. Now, we used ionic potential, right, to make some predictions of what our cations or how our cations are going to behave, right? That's the whole potential here, is that we used ionic potential just as a tool, right? And ionic potential is 2 simple properties: the charge of the ion over its ionic radius. And from that, right, we can come up with some ideas about how these cations are going to behave once they're leached out, or sorry, once they're weathered out of our primary mineral. Now, when we're talking about the fates of anions, we are talking about, in our incongruent dissolution reaction, there's 2 common ones, bicarbonate and hydroxide. Right? So this is going back to our incongruent dissolution reaction. What's going to happen to these? So what happens to most anions in the soil environment over time? And I'll ask Kylie.
Sorry, I'm not sure if I really understand what the question is.
So the question is, we're trying to predict of the products in our incongruent dissolution reaction. We have bicarbonate and hydroxide. Those are common anions that are associated with that reaction. So what's a likely fate of those things, and what's a likely fate really of any anion that we might have in the soil? I guess the question is it going to be attracted to negatively charged soil particles?
No.
No, right? Because it's got the same charge. And so if most soils have a negative charge, we have these anions that are present, they're going to be repelled by that negatively charged soil. And so what's going to happen largely is they're going to leach. And since both of these, right, are conjugate bases, right, or hydroxide's a base, and soils become more acidic with weathering, what's going to happen is that they also can be neutralized. Right? And so if they're going to become neutralized, that hydroxide, right, is going to become water, and the bicarbonate could become carbonic acid. Okay, so that's a likely fate of our anion weathering products of incongruent dissolution. They're just going to be lost, right? They're going to leach because water is going to be moving through the soil environment. They're not attracted to the soil particles like calcium, magnesium, potassium, and sodium, so they're easily removed from the system. Okay, so let's do this now. This is a pretty cool part of the class that I like a lot. So let's talk about how we can measure the degree of weathering in the soil environment. Okay, so quick, simple way to do that. And I will show you this. I'll show it to you. Okay, wait a second though. So let me set the stage. I don't know if you watched Breaking Bad when it was going, but Breaking Bad was a show about a teacher who turned into a meth maker and dealer. He's a chemistry professor, and he ended up like going down a really bad road and did a lot of bad stuff. And one of the things that they did, and what this is demonstrating, is why hydrofluoric acid is needed to dissolve stuff. And so what they did in the show is that in order to get rid of somebody that they had murdered, they dissolved that person in hydrofluoric acid. So that's what this is showing. Okay, but they don't show the details associated with it, right? They just show like why you need hydrofluoric acid and then what happens when you have hydrofluoric acid and you put it in a bathtub with a person in it. Okay, right, real quick, what hydrofluoric acid does, and the reason why I'm showing you this is because hydrofluoric acid is a super strong acid. Fluorine, as you know, is the most electronegative element in the periodic table. And so in order to dissolve stuff that's very difficult to dissolve, you need hydrofluoric acid. Okay, and that's kind of the context for this right here. But let's see. Okay, so when we're going to measure or assess the degree of weathering, we're going to take soil and dissolve it in 3 acids, right? And those 3 acids that we're going to use to dissolve the soil is hydrofluoric acid, hydrochloric acid, and nitric acid. So a combination of those 3. And when we do that, that can dissolve even the most stable mineral. And the most stable minerals are those minerals that contain silicates, right? So quartz is super difficult to dissolve. You can't dissolve quartz-rich minerals without hydrofluoric acid. Okay, so that's the tie-in to that short clip that we saw of Breaking Bad. So we take a soil, right? And we want to determine the extent to which weathering is occurring or has occurred. And so what we do is we dissolve that soil and then we measure the quantities of silicon, iron, and aluminum. Okay, and we look at those as a ratio. So we look at those in terms of the silicon concentration divided by the iron concentration plus aluminum concentration. Okay, and this gives us an idea of the extent to which weathering has occurred in that soil. Okay, so what do you think for the most weathered soil? What's this ratio going to be? Is it going to be low or high? And think about that question in terms of desilication.
Low.
Okay, what's that?
It's going to be low.
It's going to be low, right? So weathered soils will have a low ratio, right? And the number that we look at, sort of the cutoff or threshold number, is 2. Okay, so ratios less than 2 are pretty highly weathered. Ratios greater than 2 are not so highly weathered. And why is 2 kind of a key number here, do you think? Robin Pearson and company.
I'm not quite sure. Could you rephrase the question?
Yeah, absolutely. So our threshold number, right, that we're going to use to judge how weathered a soil is for this ratio is 2, right? That means we got 2 times as much silicon as we do iron and aluminum, right? And so my question was, why the number 2? Why is that kind of a key threshold number? That's a hard one.
Because you have twice as much silicon?
Yeah, you got twice
I'm
as
not sure.
much. And what type of soils are going to have twice as much silicon as iron and aluminum? Those are soils that are going to be composed of 2-to-1 phyllosilicates. Right? And so as things weather and develop, right, we have our primary minerals. Those primary minerals are going to weather into some secondary minerals and largely 2-to-1 or 2-to-1-to-1 phyllosilicates, and then 2-to-1 phyllosilicates. And then what are 2-to-1 phyllosilicates going to weather into if we're losing silicon?
Is it a 1-to-1?
Yeah, 1-to-1, right? And so what's the ratio of a soil for the silicon to iron and aluminum going to be when you have 1-to-1 phyllosilicates largely?
1.
1, yeah, right? It's not rocket science. Makes sense. You know what I mean? Totally makes sense. And then our 1-to-1 phyllosilicates are going to weather into iron and aluminum oxides, right? This is the typical weathering sequence. This is what happens as we get more and more desilication taking place, right? Along that trajectory, right? I mean, like, this fully makes sense, right? And so we can use this ratio as a tool, right, to understand what's happening in our soil. Okay, let's take a look at a couple soil profiles then. Okay, here we're looking at a young soil. What is our silicon to iron plus aluminum ratio going to be in our A horizon? Greater than 2 or less than 2? If it's greater than 2, you can just say this. If it's less than 2, you go like this. Greater than 2, right? Greater than 2. In our BT horizon, greater than 2. B horizons are zones of accumulation. So this is where we're going to accumulate stuff. BK horizon greater than 2. BKQM greater than 2. R horizon greater than 2. Right? A mildly weathered soil is going to have a silicon to iron and aluminum ratio of greater than 2. Okay? How about this soil right here, moderately weathered? Now let me ask you this, Steve. Where in this soil have we had probably the most intense amount of weathering take place? And I'll give you some hints. Is it the topsoil or the subsoil? And you can think about this in the context of where do you have the greatest quantity of microbial activity, the greatest quantity of rainfall hitting the soil and moving through it? Like, where does that all happen?
In the subsoil?
Close.
Topsoil.
Right? So the most intense weathering for a soil is usually in the topsoil, right? Because that's exposed to environmental conditions. So at the topsoil, we might have a ratio of less than 2. What about our E horizon? I'll go on to Nicole. What might the ratio of silicon, iron, and aluminum be in the E horizon? The E horizon is composed mostly of sand.
I'm just gonna say greater than 2.
Greater than 2. And also, as soils weather and develop, things weather in the surface soil and leach out of that surface soil, and the thing that's going to weather out of that surface soil is silicon in the form of silicic acid. It's going to move down the soil profile, and oftentimes it's going to reaccumulate, right, or reprecipitate where there's less water. But the E horizons are typically composed of sand, which is quartz, and so our ratio is going to be greater than 2. And then below that, right, if this is a moderately weathered soil, probably maybe around 2, right? We'll have largely 2-to-1 phyllosilicates in our BT horizon. T means accumulation, right? Alluvial accumulation of clays, right? Mostly aluminosilicate clays. And I know that our time is up, but just let me show you one more slide, okay? To finish this point. So now we have our very weathered, highly weathered tropical soil. We have 1-to-1s, 2-to-1s, or oxides of iron and aluminum here.
Oxides of
Oxides,
iron
right?
and aluminum.
Oxides of iron and aluminum. And so our ratios are all, I know you can't see that because my pen's writing in red, but every horizon less than 2, right? Because there's been intense weathering. The silicon's been leached out. It's formed silicic acid and it's been removed, right? And that, right, is one way that we can predict it and predict the extent of weathering. And that is a beautiful thing that just happened to all of us just now. Okay, when we're together next time, we're going to talk about prediction of ion mobility using these 3 frameworks. Okay, so for those of you who have lab right now, let's meet in the loading dock at 1:15. Okay, so you got like 15 minutes to regroup, prepare yourself mentally, physically, and emotionally. Okay, and if I don't see you today, I'll see you tomorrow. Have a great afternoon.
Thank you.
Thank you.
Thank you.
Hi, thanks.
Thank you.
Welcome.